Hello, everybody. Welcome back to the second of two posted lectures for climatology for week 7 in lieu of my absence at some department stuff on Wednesday. And right now, I should be sitting in a hydrogeographies section in Westlake's AAG. So hopefully I'm enjoying that and having fun. But in my stead, you are obviously watching these on YouTube. Um, just our last snapshot of this week, week 7. Still don't know how we're moving past this quickly. But today you have your quiz and climate connection due, as well as your discussion post 3 response. You can see all of those here. Don't forget, as I completely forgot to fix, your final project topic is due Sunday, the 29th of October, not Friday. I goofed that up on the last one and forgot to change it because I was recording these back to back. So apologies. But Sunday, the 29th of October, 11:59 p.m. is when your final project topic uh, assignment post response is due. Everything else, climate connection, quiz, and discussion are due today. If you're watching this as it premieres at like 11, your quiz will open at normal time at noon. So the last lecture we were looking at surface-based react or responses for modifications to these idealized general circulation patterns that we've been talking about. Now we're going to look at upper level airflow and secondary circulation patterns. This should be a little bit shorter of a video, just the amount of stuff I have in here and whatnot. So sit back and, as I mentioned before, kind of pause as you're going along just to make sure that you write everything down. Then you can listen to me, and then you can add and annotate based off of what I've already said. Might make your lives a little bit easier. So first thing, for upper level airflow, we need to make a couple of assumptions, right? Uh, First off, frictional forces are not a driver, are not really a factor when it comes to upper level airflows. The Coriolis effect and the pressure gradient force are. But frictional forces are those imparted from the surface. And if we're in the upper level airflow, we're assuming that we're in the free atmosphere and that frictional forces are negligent or non-existent. The other thing, flow in the upper level mid latitudes is primarily westerly. Pardon me. We'll talk about that a little bit more as we go on here. So why is it that these winds are westerly, or what drives that? Well, if we think of a parcel of air, right, we're going to look at it here. Um, there's a pressure gradient from north to south. We know that. And we're dealing with winds aloft. So these are winds moving from the mid latitudes north towards the poles. Our pressure gradient force is pushing those winds, obviously, towards lower pressure, equilibrate. The Coriolis force is pushing perpendicular to those winds, right? So we're deflected. And the further north we go, the stronger that Coriolis deflection is having an effect on the wind, right? So it would move our little parcel of air so that winds were blowing out of the west, westerlies. So if we're looking at upper level airflow, one of the ways that we can characterize it or talk about it uh, is based on the what we call the amplitude or the waviness of the flow pattern. Um, so how it's doing that, right? De-amplified winds or nearly straight winds that follow a west to east pattern, westerly flow, remember, west to east, are what we call zonal winds. Uh, those with significant latitudinal amplification or waviness And mid-latitude flows are what we call meridional winds. We're going to see what each of those look like in a couple examples here in the next couple of slides. So winds aloft, here we're looking at winds in the northern hemisphere. Same kind of thing, pressure gradient going from 520 millibars to 496 millibars, so we're looking at that 500 level. If winds are just straight line, we call these more or less geostrophic winds. If they're relatively straight, evenly spaced, and parallel to our isobars, our pressure bars, rather than perpendicular to them, they're geostrophic winds. These are generated when a balance is reached between the Coriolis force and the pressure gradient force. If these winds follow predominantly west-east patterns, we call them zonal winds. Now, any portion of the mid-latitude wave that dips towards the equator is termed a trough. So if we don't have zonal or geostrophic winds, if we've got these meandering flows like you see here, we can see a couple of different features. The first is called a trough, and that's this portion here, right? The valley of our wave. The ridge is the top portion, right? The peak. We call that a ridge. Now, troughs and ridges are associated with low and high pressure systems. They're different than cyclones and anticyclones, though, so we need to make that key distinction. These are elongated zones of pressure without that cyclonic motion. Where the isobars for circular cells of either high or low pressure follow this curved path and winds flow roughly parallel to the curved isobars, we call these gradient winds, which result from the balance amongst the pressure gradient force, the Coriolis force, and centrifugal winds, or centrifugal forces in winds aloft. These can lead to meridional winds, which predominantly follow a north to south flow pattern. So these are important features, and we'll learn a little bit more about them as we're putting together all the pieces of our puzzle and looking at how things over continents and ocean basins and all that flow from a regional perspective. The next thing, and this is a really key one to talk about, are Rossby waves. I've alluded to these in the last couple of lectures. These are very long waves. So atmospheric waves can be described according to their wavelength. So the distance from peak to peak. Those with wavelengths of hundreds of kilometers long are called long waves or Rossby waves after Carl Rossby. Rossby waves define the polar vortex. That's what we're kind of looking at in this figure from our Encyclopedia Britannica off to the left-hand side here. We can see 3 to 4 waves in winter when the thermal gradient is maximized, up to 6 during the summer, but their amplitude is severely decreased. So these tend to be less meridional, so less of that kind of north to south flow, or south to north, depending on which hemisphere you're in. In the southern hemisphere, there's less things in the way, more ubiquitous conditions over the oceans, for example. Now, these ridges and troughs, what you're seeing develop here, particularly in that 2 and 3, the top right and bottom left panels, for example, are really essential in the energy balance within our hemispheres. Because if we didn't have them, we would essentially see energy differences that would increase between the tropics and the poles. The poles would become progressively colder. The tropics would be progressively warmer until there was like a restricted, narrow little band of hospitable land for life to live in. So it's because you've got that area around the pole or around the equator would just continue to heat. That area near the poles would continue to chill, and the ridges and troughs are what bring that air down and bring it up and drive these kind of broader energy distribution and circulation patterns. So, what impacts Rossby waves? Well, vorticity is a really important one. Um, this just represents the rotation or spin of any object. There's a few different ways to look at vorticity. Um, you can look at it from a planetary sense. We all have some level of vorticity imparted on us by the rotation of Earth. Particles in the atmosphere are always rotating because of this planetary vorticity, and it's proportional to the Coriolis effect. So, and the poles, maximum spin or maximum vorticity. Near the equator, none or reduced vorticity. Uh, but other things have vorticity as well. You can, if you were to hold a pen, for example, and spin it between your fingers, well, there would be a relative vorticity there. Or if you were to hold it and spin yourself, there would be vorticity there as well. So there's different forms of vorticity. We're not going to focus too heavily on this. Um, we are in just a little bit here in the next couple of slides. I'm talking about constant absolute vorticity trajectory. Absolute vorticity is the sum of the relative vorticity and the planetary vorticity. So local factors driving vorticity and planetary factors driving it. Somewhere between, and the important part, the reason we care about this is somewhere between cyclones and anticyclones, there is a level of non-divergence. Neither converging or diverging winds happen here. Um, right around that 500 millibar level is a good approximation of where that is. And it follows a constant absolute vorticity trajectory. So preferred geographical areas exist in Rossby wave patterns over time where flow adjustments occur. And pairs of locations where ridging and troughing occur simultaneously are called action centers. So this is all we really care about in this sense, is that some places where these ridging and troughing events occur regularly, we call them action centers. And that's more of what's driving things that are expressed through climate. So flow over mountainous terrains can have an impact on Rossby waves as well, because mountain areas vertically constrain our atmosphere. So air is piling up on the windward side, so you're seeing an increase in pressure. Expanding on the leeward side, you're seeing a decrease in pressure. So that impacts the way that our wind is moving as well. Baroclinicity is another factor. So baroclinicity is just, by definition, intermixing of steep thermal gradients across small regions that leads to changes in Rossby wave flow. This is typical along coastlines. It's even more typical on the leeward side of mid-continents or mid-latitude continents during winter, because you have the cold, frigid air from the continent encountering the warm western basin currents and cold continental air kind of coming together. So you have a very steep thermal gradient, and that can impact and change the location of these Rossby waves. And then airflow around the polar features areas of extremely fast flow. So our polar front jet stream, really. It's this enclosed region that represents our circumpolar vortex or polar front jet stream. Strong winds aloft that enclose our polar high. So the polar front jet stream marks the periphery of this circumpolar vortex. So the extent, really, of the circumpolar vortex. We saw where the polar jet stream was, kind of at that meeting point around 45 to 60 degrees north and south. It migrates over time throughout the seasons, but one of the features of that polar jet, something we call our jet streak, and that's the region with the greatest wind speed. This occurs over baroclinic zones, so where you have these steep thermal gradients that exist at the boundary of circumpolar vortices. So that. And then these last few slides, and like I said, this is going to be a bit of a quicker one here, are looking at how Rossby wave flow changes over the year. So we're going to look at January, April, July, and October, I think is what I have here. So notice these are going to be the same views on each of the 4 slides. And this is the mean 500 millibar geopotential height in the northern hemisphere. So that's what we're looking at here. So notice in January in the southern hemisphere, pretty straight, right? Very bumpy and wavy during winter in the northern hemisphere. We see that it's a little tough to see, but we can see like the 5,800 line is dipping down into Mexico, whereas the 5,200 line extends over northern Canada, the Northwest Territories, and northern Russia. Here in April, we can see that because in the northern hemisphere, our polar jet is suppressed. If we remember from our Wednesday lecture, we see that 5,800 line is getting into northern Mexico in the Baja Peninsula, and that 5,200 line is a little suppressed. It's not really over the continent as much, over some of the islands in the north. And we see kind of some changes in April, kind of some waviness in the bottom portions in the southern hemisphere. And we see, again, some deviations, especially over the northern Pacific, coming into towards our summer. July, here's our summer. We can see that 5,800 line is now up in northern United States, throughout the Great Lakes region, into southern British Columbia, and then kind of pushing into central Russia as well. We don't see that 5,200 line. Everything's kind of getting compressed again in the Arctic Circle region. And then in here we can see in October, see it's starting to push just a little bit, kind of consistent location. We can see that line kind of in that 5,800 line, kind of in the center of the United States, again, pushing a little bit south. So that's all I had for this one. Kind of a short, easier lecture here. If you need any review, I do invite you to look at the textbook, just because obviously I'm not in person, so that you can't ask questions. But feel free to ask any questions or shoot me an email. I'll be on my email, but obviously it's going to be a little tough because I'll be in sessions and with students and all that kind of stuff. So I will talk to you all on Monday. Class is normal. Hope you have a good weekend, and we will see you then. Thanks. Bye.